Hi, my name is Sebastian Ochoa, and today I'm going to be talking about an interesting discovery that scientists at Berkeley have found about pathogen evolution. Homology modeling is used a lot to make a 3D structure of a protein, and it's known to be very accurate, but there's a problem. There's many steps to homology modeling. You need a protein that has an unknown structure and a solved effector structure. After this, you can continue on to make the model. In case you're wondering, the effector structure that I'm talking about is just a small molecule that binds to a protein that can change the way that it works. You start to see the problems when you think about how they have to solve each effector structure, find out what it is before they make the model because it serves as a template for the protein. Taking into consideration how many molecules it could possibly be, it makes it just so much worse and so much more tedious to find exactly what it is. What you see in this graph here is a bunch of proteins and with their solved structures already in. You could see the precision of each point of each protein, and it just shows all the information you're getting that's completely automated. The precision, everything about it was completely automated by a computer. And this next list is just a list of all the proteins and structures that were found with this system. And all of this is automated. You could see how much information they really got from this. This new system gives us an opportunity to predict what these effectors are with the computer, which automates it, makes it so much easier for you to find it. This already gives you the template to make the protein, just makes the job a lot easier. These two colleagues at Berkeley were using this method, and they found 500 new models that have been unpredicted earlier. This gives more information on solving these effector structures. But why is it so important? When you ask this question, I really have to just talk about what these models even do. They just show you the protein and its amino acid sequence. And there's a lot you could do with that. Now, I bet there's plenty of things that we can use this for. But I'm going to bring up something that we've been talking about in class, which is the mRNA vaccines. To make these vaccines, you have to look at a person and you have to look at the protein that they can't make. And it might be because of mutation, it can be whatever. But with this vaccine, of course, you have to put in some RNA that will force their body to make this protein. And this is why the model is so important. This model allows you to look at the amino acid sequence that makes a certain protein that a person might need. And that's just one thing you could use it for. I bet there's plenty of things you can use it for, but this is just one example. The two colleagues that came out with this information stated that this is going to become a lot more common and that it's going to be used a lot more because it's just so much easier. One thing I would like to say is that it still isn't as accurate as homology modeling because it's not as developed. There's a lot of improvement. But we have time and I'm really excited to see where it goes. The main idea for this presentation is that homology modeling is used a lot to make a 3D structure of a protein, and it's known to be very accurate, but it needs known structures which takes a long time to get. This new system automates it and makes it easier to gather information about proteins. The future ramifications is to inform people about computational structural genomics, and the biological discipline is molecular and computational biology. Thank you for watching.